for joining us for this ECIS webinar dealing with automated cell migration assays. My name is Charlie Keese, and I'll be your host for this approximately 30-minute long webinar. Sometimes the slides may update slightly behind the audio. Please just be patient if that happens. The idea of monitoring cells electrically came about a number of years ago when Ivor Gaver and I were at the General Electric Research and Development Center. There we realized it was possible to use very weak AC signals, growing cells on small electrodes and monitoring the impedance, and from those signals we could detect morphological changes going on in the cells. This was published a long time ago, back in 1984, and it remains the basis of the technology that we market today. We have several different ECIS electrode arrays. They're the heart of the system. This is actually one that has 8 wells, as you can see in the upper left-hand panel. The center panel, you see the actual electrodes involved in the measurement. In this case, we're using a very small 250 micrometer diameter electrode in the center of the well. Of course, it's an electrical measurement, so we have to complete the circuit, and so there's a large counter electrode labeled CE. But the impedance goes up as the area goes down. And so in this case, the only cells we see are those located on that small 250 micron diameter spot. The impedance of the counter electrode is so low we can ignore it. Actually, this is the type of array that most of the data I'm going to show you today will be taken with, because we need this very small defined area to wound. When we make the measurement, we apply a very weak AC signal normally. This is because we want the measurement to be non-invasive. Currents are in the microampere range, and the voltage drop across the cell membranes is only of a few millivolts, and usually this is oscillating back and forth several thousand times a second, and so the cells are unaware of this measurement taking place. But they do alter the impedance. If we apply a known current and monitor the voltage, we can take the voltage, divide it by that current, and we come up with the impedance, which is measured in ohms. And this is just an AC equivalent of Ohm's law from Physics 1. But you may also remember from studying physics that when you have an AC signal, it is a much more complicated measurement in that there can be what we call phase differences. Let me see if I can explain that. Here we're seeing a graph that shows the current being applied at a certain frequency, and that's indicated by the red dotted line. We monitor the voltage. That's indicated by the black solid line. But notice the two do not peak at the same time. We would say that the voltage is lagging the current by a certain number of degrees, thinking of the total sine wave here as one cycle up and down as 360 degrees. Knowing that angle and the amplitude of the voltage, we can break the impedance into its components, namely a resistive portion and a portion due to capacitance, which is coming from the gold metal electrodes being affected by the capacitance of the cell membranes. This is typical data we would see if we inoculate one of these small 250 micrometer diameter electrodes with 2 different types of epithelial cells in this case, BSC1 cells and normal rat kidney cells. First, look at the bottom trace. When there are no cells added to the well, the resistive portion of the impedance of the electrode remains constant. It's unaffected, very quiet. Now, when we look at what happens when the cells attach and spread, we see the resistive portion of the impedance changes dramatically. And incidentally, this is being measured at 4,000 hertz. That's the frequency of the current. BSC1 cells attach more readily than the normal rat kidney cells. They both come to the same final resistance. This would not necessarily be true of all cell types, but these two happen to. And also notice that after the cells have formed a confluent layer, because we're adding enough cells to go to a complete layer, we see what we call micromotion. Excuse me, I didn't mean to click there, which is this fluctuation on top of the signal, which is due to the movement of the cells. Again, we see that because we're only looking at about 50 cells that can crowd onto this small circular electrode. Of course, many times you'll want to monitor additional numbers of cells. That's usually the case in using ECIS, but for today's wound healing migration talk, we'll be mainly looking at that small, single 250 micron diameter electrode. But as you can see here, there's what we call an 8W10E that has 40 electrodes. There are 96 well plates that have interdigitated electrodes that monitor several thousand cells to give good statistical accuracy. Here's the difference between inoculating one of these single electrodes and, say, the array that has 40 small electrodes all being measured. We're monitoring the resistive portion of the impedance, again at 4,000 hertz. And notice we're dividing everything by its starting value. We call that the normalized resistance. All of these curves come out at 1, which is indicating that, and there is a confluent layer there, but we're still calling that 1. A couple hours into this run, we change the medium. And notice the cells respond with about a 30% increase in their resistance. But what is obvious here is that when we look at the 1E electrode, which is the red trace, we're only looking at 50 cells. And so we see a great deal of this random motion going on in this small population of cells. Excuse me. But when we have 40 electrodes, 40 times the number of cells being measured, although we see the trend of the resistance going up and coming down as the cells adapt to the new growth factors and so on in the fresh medium, we can eliminate most of the micromotion. For today's work, though, we're interested in that 1E electrode, that small population of cells. We see these changes because the cells are going to interfere with current flow. In this next slide, we see the red arrows indicating current being carried from the electrode, which is defined by the insulating film. It's being carried by ions. As the cells come down, they attach and spread across the entire bottom of the well. But a few of them end up on that small electrode. The current is maintained constant. And if we look in more detail, in this cartoon version of 3 cells, the current has 2 different paths indicated by the solid and the dotted red lines. The solid line is showing that the current, carried by ions again, can simply flow beneath the cell around the adhesion plaques and through the paracellular space between the adjacent cells. But notice there's the dotted line that goes right through the cells. And this is to indicate that some current will couple capacitively through the cell membranes, much as in 2 metal plates in Physics 1, thinking about a capacitor, an AC signal effectively can pass through the capacitor by charging and discharging the different metal plates. We're not talking about current being carried through ion channels. They're many too few, and they're too small to account for any part of the measurement we normally see. We instead are coupling by charging and discharging the membrane of the cell very rapidly at usually several thousand hertz. When anything changes the morphology of the cells, those paths, in particular the ones under and between the cells, can be altered by a morphological change. The same is true if the membrane becomes more convoluted and there's more surface area, the current finds an easier path by coupling through the membranes. So anything that affects cell morphology is something that usually will be reflected in the ECIS measurement, from looking at cytopathic effects of viral infections, signal transduction, changing respiration, adding different drugs, of course, changes in the physical conditions, and so on. It's a very useful morphological monitoring system. But today what we want to talk about is cell migration. And let's begin by thinking about the traditional wound healing assay. Commonly, this is done by growing a layer of cells to confluence, taking a needle or a pipette tip or some other object or maybe a small spinning disc and removing a group of the cells, leaving an open area. The cells, being alive, realize there's an open space, go through whatever signal transduction is necessary, and begin to migrate in to heal the wound. Ultimately, they fill up that space. And by monitoring the time it takes the cells to do this, we can talk about a rate of cell migration. This is done by taking several images usually and using either image processing or other more sophisticated ways to look optically at these changes. But they're difficult, usually hard to reproduce, and difficult to quantify. When we make the normal ECIS measurement, we apply only about a microampere of current. This is, again, non-invasive. The cells are unaware that they're being monitored. They show no changes from that weak current. But if we up the current, instead of at a microampere, 1,000-fold higher to the milliampere range, this causes a small voltage drop across the cells of only a few volts, but that is an enormous electric field, and the membranes break down in a very well understood process called electroporation. If we leave this elevated current on instead of for just a fraction of a second to electroporate the cells, but rather for several seconds, we get severe pore formation, possibly a bit of localized heating beneath the cell, but whatever the cause, we kill the cells on the small electrode. Let me show you some pictures to show that we can electroporate the cells first. Here we're seeing cutouts of that small electrode covered with confluent layers of MDCK cells. We give them this high current pulse of a milliampere, and this is always applied at high current to protect the electrodes. So we're using 40,000 hertz, 1 milliampere current. If we apply that for different lengths of time, seen underneath each of these figures of the electrode, we see that by 100 milliseconds, we're taking up a membrane impermeable dye, lucifer yellow, that's been added above the cell layer. But once we get up to a fifth of a second, 200 milliseconds, or a half a second, 500 milliseconds, we're starting to see areas where the cells are dying. To show that's really cell death, we also have done vital staining. Again, I circled that 40,000 hertz to remind you that this is not the measuring frequency, but this is the frequency that's used to carry out the wounding. Here's the vital stain data. We see cells prior to wounding, immediately after wounding, and then 2, 4, and 6 hours after wounding. We've stained the cells with the vital stain calcine AM, the green stain, and also with ethidium to light up the nuclei if the membranes are compromised and that dye can find its way to intercalate in the DNA. And what we clearly see here is that prior to wound, we see the green stain in place, very little ethidium lighting up in the nuclei. After wounding, again, the calcine AM is mostly absent from that small electrode, whereas the ethidium is a strong signal. As the healing goes on, we eventually return to the look of the cells prior to the wounding. So we are killing the cells. Here's another look at this using scanning electron microscopy, and these are NRK cells that are being wounded. You can see it's a confluent layer in the upper left-hand panel. You can see the outline of the electrode. Immediately after wounding, another scanning electron micrograph is taken, showing that a great deal of disruption has occurred at that small electrode. And now we know those cells, in fact, are dead. They can be swept away. And then in the lower two panels, we see the same sort of wounding and healing taking place before the layer is completely healed. And finally, in the last lower right-hand panel, upon complete healing. Here's a look at an electrode following wounding where we have swept the cells off by just using a light stream of medium. The important thing to see here is that we have an extremely well-defined wound, a little 250 micrometer island in the middle of a confluent layer, where the cells can then migrate in and heal the wound. So what we're doing with this ECIS method of monitoring cell migration is replacing the mechanical scrape wound and some optical observations with a totally electric method where electrical wounding is carried out at high current, but then the cell's recovery and migration is monitored at the low non-invasive currents. The neat thing about this assay is that it can all be done without even opening the door of the cell culture incubator. Here's what we see when we have 4 confluent layers of electrodes. We apply this high-frequency, high-field pulse a couple of hours into the monitoring. We're just following the impedance at, I believe, at 16,000 hertz here. And what we see is that when 2 of these electrodes are wounded, they immediately drop to open electrode values. And then, over the next few hours, as the cells migrate in from the periphery of that wound, we see the impedance climbing back up to control levels during the healing process. And so, if one simply looks at the time it takes from wounding to the return of these curves to control levels, which is about 7.2 hours, and if we think of the cells moving in at a fixed radial speed, they have to go 125 micrometers to get to the center of that electrode. We simply divide that distance by the time to get a migration rate of 17 micrometers per hour. The beauty of this measurement is shown in this slide because this very precisely defined wound is extremely easy to achieve. Here we have, again, several confluent wells at time 0. These are BSC1 cells. Again, they receive a high field pulse shortly after the start of this run, and that pulse is applied for different periods of time. The first one where it drops and comes back is 200 milliseconds. The one with the orange arrow is 1 second. And then the other 3 are 5 seconds, 10 seconds, 15 seconds, and we can actually expose these cells to as long as several minutes of this high field pulse. The wound and the healing stays very precisely defined. What we're seeing in the one that's called electroporation as some damage is where we have partially killed the cells on the electrode. Some are surviving, so the wound healing is not a really complete assay. But the important point again is it's very easy to apply the wound healing current. The timing is not critical. The wound remains the same. Here's some data in the literature where ECIS has been compared with more traditional methods, the scrape method. I'm not going to go through the details of this experiment. The important thing to see is that in this scrape wound assay, an open area that's approximately 1 millimeter in width has been scraped through a confluent cell layer. In the case of the control and the vector that's been added, these cells move approximately 1/3 of that distance in a period of 16 hours. So if you do the division, that's about a 20 micrometer per hour migration rate. Notice in the case where we have the MEK5DD, there is no migration. We blocked migration, and this is a JBC article you can look up if you'd like to know more details. The same experiment, though, in this paper was done with ECIS. Again, In this case, no migration. In the other case, about 20 micrometers per hour. Here's the data with ECIS. The pulse is applied to the confluent layer of cells. In about 6.1 hours, we see the vector and the control returning to control levels. Whereas in the case of the MEK5DD that showed no migration, we again see the reduction of the cells down to open electrode values, but there is simply no return to control levels. And if we take the 125 micron diameter of the electrode that you can see in the lower left-hand part of this slide, divided by that time, 6.1 hours, we get 20.4 micrometers per hour. Exactly the same, or certainly within the range of what was seen in the more traditional scrape wound, suggesting that the mechanism of wounding in both cases is not important. In one case, we electroporate. In the other case, we mechanically pull off the cell layer. Here's another example of mesenchymal stromal cells in conditioned medium that is promoting cell migration. Again, we have the impedance data compared with more traditional measurements of wound healing. Again, in agreement. Yet another paper in a JBC 2015 article dealing with a knockdown of a subunit of the sodium-calcium exchanger. We're regulating epithelial cell migration, and again, scrape wounds and ECIS data shown in a histogram here. Again, agreeing in terms of the migration of these cells. The method is very reproducible. Here, 4 wells have been wounded. They return to control levels. They're rewounded, and you can see again very, very subtle differences in the migration as these cells are spending longer times in culture. It of course depends on the type of cell. Here we see a wound with BSC1 cells, and here with the NRK cells. Here's an example of drugs affecting migration. These are confluent layers of cells that are in the presence of different concentrations of DMSO that you see listed here. The control is the light blue, and they're wounded at about 12 hours into this experimental run, and we see them coming back to control levels. But notice in 2.5 or 1.25% DMSO, the migration is greatly reduced as it's requiring longer for these cells to return to their control levels. There's another aspect that's a little different about the ECIS wound healing assay than the more traditional scrape wound. For example, suppose that you had put down fibronectin on your cell substrate and grown the cells to confluence before scraping through the cell layer to do the migration assay. Once you scrape through the cell layer, any protein that's been absorbed on the electrode is also being removed. It's just a monolayer of protein. More proteins will go in and absorb naturally to that open area, but as the cells migrate in, then they're migrating on serum proteins, not on the fibronectin you pre-absorbed on the substrate. With ECIS, though, and the wound healing assay, it's different. Here we're looking, and I apologize, we're looking here at capacitance, which is another way to monitor cell coverage. It's data that's given out all the time by the instrument, and it can be related to the degree of cell coverage, but as cells go down, they block the electrode capacitance, and when you wound them, the capacitance comes up. So these are kind of inverse curves, but they're still showing cell migration, just as the curves we were dealing with previously with resistance. And here, before the cells were inoculated, electrodes were coated either with bovine serum albumin or gelatin. And notice we are seeing an effect on the migration based on the protein coat. So let me show you some of the problems you can encounter with this electrical wounding assay. And here's one of them. Again, we're looking at capacitance, which goes up during the wound, comes back down as the layer is filled in. First, with BSC1, we have a very nice wound healing assay. Cell-covered electrodes go up to cell-free, return to cell-covered electrodes in a certain period of time. We're following 8 different wells here, and you're seeing the average. But there's another cell line, and I can't remember what this one is. We're calling it cell line A here, which is typical of cells that don't work well in this assay. In this case, the wound is usually effective. The cells are killed, but often the cells fail to move into the area. And we believe this is usually due to the fact that some cells, after wounding, remain stuck to the electrode. For example, here's an electrode that's been wounded. We've attempted to clean it off, and you can see there are several cells still on the electrode surface. If you do time-lapse cinematography, you will see these cells are no longer alive. They're not moving, but they nevertheless are present and may block the incoming cells from occupying that spot, and they are not blocking the current very effectively. We found there is a way potentially around this that we call the electric fence. And this is a new approach that's built into all of our instruments. So you can try this assay. And here's the idea. We've inoculated cells on these small electrodes at time 0. You can see the control going up and the micromotion as it oscillates back and forth. The other red, blue, and green traces are also wells that were inoculated at the same time, but they are receiving every 5 minutes, I believe, a small high current pulse, and that is preventing the cells from coming in and attaching to the electrode. We've used a fairly light inoculation. If we were to look at those electrodes here in this situation, the control where up above in this figure, the lower one where it's been fenced for 42 hours after inoculation, and although a few cells seem to have accumulated on the edge of the electrode surface itself is not compatible for cell growth. So here's the critical experiment. We turn on the electric fence, and at a certain period of time, we turn it off. And when we do that, we find the cells are ready at the edge to move in and migrate to heal the wound. At the same time we turned off the electric fence, we also applied a high current pulse to the confluent layer of cells. And you can see them dropping down and then coming back. Notice the migration rates are approximately the same in these two cases. The only interesting difference here is that when we wound the confluent cell layer on the electrodes, notice there is a very slight lag period before the cells begin the climb upwards. And this may be due to the fact that some signal transduction has to take place before migration can begin. So that's an interesting difference. That's what I wanted to cover today. These measurements are all made with the instrument we refer to as ECIS Z theta, Z for impedance, theta for the fact that it measures the phase angle. And all of this work is done, measuring these things is done just with very user-friendly software where you simply choose default conditions for wounding, which usually will work very fine, and follow the cell layer over time. It's possible also to monitor endothelial cells under flow conditions, their flow arrays, and one can actually wound the cells in these flow situations, which is very interesting, and study how fast cells migrate under flow, similar to that of the shear stress that these cells would see in vivo. We also have adapters that will allow you to simultaneously do time-lapse cinematography and ECIS measurements if that's something you wanted to also carry out. This is simply a stage adapter. One would have to, in this case, incubate the stage, incubate the microscope effectively. Our website is biophysics.com. If you go there and click on cell migration, this will lead you to a great deal of information that we've already talked about, some extra, and a list of publications that's quite extensive where people are using this as a replacement for more traditional ways of optically monitoring cell migration. Here are the names of some key people. If you're interested in learning more about pricing, cost of arrays, we would always insist that you demo an instrument without charge for a few weeks before you commit to buying, and they can tell you more about those arrangements. If you'd like copies of these slides, I'm happy to provide them for you. You can see I am Keese at biophysics.com down at the bottom. Just ask for them, and we'll send them out to you. You can use them in your talks if you find something useful. And I'd like to remind you that in 2 weeks from today, November 17th, we'll have our election settled, hopefully here in the United States. And that will be dealing with measuring the permeability of cell layers, or the barrier function of endothelial and epithelial cell layers, using ECIS technology. It's usually a popular topic, and that's 2 weeks from today at the same time. I'm going to put these names up in case you want to copy down any information. I want to thank you all for joining us today. We don't open this up to discussion. It tends to be a little confusing to get questions coming in, but we're happy to deal with them either in a phone call or an online text. So please feel free to contact us. I want to thank you all for joining us. Stay safe, and we look forward to hearing from you in the future. Thanks, everybody.